right, for today's Unit 8 notes, we're going to move on to Target 2. Target 2 is still solving systems of equations. Now we're learning a new method to solve, which is solving by substitution. Now, we learned graphing already on solving that, but graphing is a great method, good method to go through. However, it's not always the most efficient or always the most useful. Graphing is nice and easy if you have lines that are already in slope-intercept form, or maybe if you have some parabolas that are nice and easy to graph, but it's not always the most efficient method, especially if you don't have graph paper, or especially if you don't have nice integer answers. They're not always going to be nice, easy answers that you can read on graph paper. So that's why we have a couple other methods to learn here. So today we're going to learn substitution. Next week, we're going to learn another method called elimination to solve our systems. So the substitution method is really like how it sounds. We are going to be doing some substituting. Now, when you're doing substituting, you can only substitute things that are equal to each other. You can't just randomly put one thing in another part just because you want to. It has to be something that's equivalent. So when I look at number 1 here, I have 2 equations for my system. Notice I have one equation that's y equals. Now, yes, it's in slope-intercept form. That doesn't really matter here. We're not graphing. But what I'm really focusing on here is that it's y is equal to this expression right here. So we're saying those two sides are equivalent to each other. So whatever y ends up equaling, it's going to be some number. It's always 3 times the x coordinate plus 2 more than that. So, and that should work for both equations because, again, you're going to have the same x and the same y that satisfy both equations there. So when I think about it here, if this is equal to y, this expression, that means, okay, I have a y in my other equation. If y is 3x plus 2, I can replace the y in the other equation with that 3x plus 2. That's called the substitution step right there. So I'm going to take this equation, the second one here, and I'm going to rewrite it, but instead of a y, I'm going to leave a blank here first, and then instead of a y, I'm going to replace it with that first equation, that 3x plus 2. Now this should look somewhat familiar. We did something very, very similar to this first semester when we did some function notation. You don't have to write this down or anything, but if you remember, we had, I'm just making this one up, like f of x is 3x minus 1, just as an example. And then I had you do like f of like 2x minus 3, again, totally making that up there. We replaced the x in that. We substituted wherever there was an x, we replaced it with that 2x minus 3. Again, it's really a similar kind of concept there. We were actually doing some substitution. This, though, isn't function notation. It's 2 separate equations, but it's kind of the same idea. So once I have that, once I replace that, the whole point of that is now I have an equation that only has one variable. Notice it only has an x. Yes, it's in there twice, but our other 2 equations have an x and a y in it. When it has 2 variables in it, you can't solve for just one of them and get a numerical answer until you find the other one. So here, if I have an equation with just one variable, I can solve it. So if you do some kind of substitution and you end up with an equation that still has an x and a y in it, you know you did something wrong. You know you didn't do something that's going to help you. So it should only have one of the 2 variables, either an x or a y, and then we solve it. I'm going to do the solving part of this kind of quicker because this is review. We can distribute right here. Keep combining our like terms together. So we get this equation, and again, this equation just has one variable with it. I can keep solving. Divide by 7. And we get x is positive 1. So yay, we have an x coordinate. However, I find a lot of people circle that and they're like, woohoo, I'm done. I got my answer. I got x equals. But we are not done with the system until, you'll notice I wrote down here, we have an ordered pair. We need an x coordinate and a y coordinate. We need to find both numbers that correspond to this system. So good, we found that x equals 1, but now we need to know what y is. If I know what the x coordinate is, though, finding the y coordinate, actually pretty quick and easy. If I look at it, I have 2 equations up here that both could help me find the x, or find the y coordinate knowing the x. So once I have that, I can take that x, and again, we're going to do substitution. I can substitute that x is 1 into the x. Now, which equation do you choose? It's actually totally up to you. I'm going to tell you on this particular equation, there is one that's probably easier. I would probably choose to solve the first equation right here for y, only because the y is already by itself right here. If the y is already by itself, it's actually a pretty easy thing to do. I'll show you, and I'll do it in the other one as well, just to kind of give you an idea. So again, wherever there's an x, I'm going to substitute the x equals 1, and we get 3 plus 2, or y is equal to 5. And now we have our full solution. Again, just to show you, I wouldn't do both. Don't do both, normally, but you can use it to help you check it. If I would have substituted the 1 into the second equation, I know it's kind of small right here, I would get 1 plus 2y is 11. We would subtract the 1. We would divide by 2. And notice we would get y equals 5. So you get exactly the same answer. Because it's a system, the x and the y coordinates should work in both of them. So you should always get the same answer. Let's try another one here. If I look at number 2, again, this time, notice I have one equation that doesn't have a y equals, but it has an x equals. Sometimes I find we get so caught up in it always being y equals because we're used to graphing that people think it always has to be a y equals. It doesn't. This one I have x equals. So now I know that x has to equal this expression, negative 2y plus 2. Those are equivalent to each other. So I can take that, what's equivalent to x, and substitute it into the x of the other equation. Again, since it equals x, we're replacing the x. So I'm going to rewrite the second equation here. 3 instead of x, we're going to replace that with negative 2y plus 2. Still the plus y, still equals 16. Everything else is the same. The only thing I replaced was the x right there. Now, you actually had a couple options. Some people like to think, like, oh, well, what if I solved this second equation for y equals negative 3x plus 16, and put it in here? You absolutely could have done that. So there's actually a lot of times different options. Number 1, you could have taken the second equation and gotten the x by itself, and we'll talk about that in some of the other ones, what might be easiest. If you already have one that's by itself, typically I'll use that one to start with. All right, I'm going to go through the solving. This gives us negative 6y plus 6 plus a y is equal to 16. Combine my like terms together and keep solving. Subtract the 6 from both sides. Divide by negative 5, and we get that y is equal to negative 2. But again, we are not done. That is just the y coordinate here. We want to take that y coordinate, substitute it back in to find the x coordinate. Again, you could do it in either of these two equations. You'll usually see me choosing the one where the x or the variable is already by itself. Again, it's just usually a little bit less solving, because here I can do negative 2 times negative 2, which gives us 4, and 4 plus 2, it's a plus right there, gives us 6, and we now know our answer is 6, negative 2. One of the best things about this unit is that you can actually check your answers very easily. You can even check them in your head. If I substituted both of these back in, again, this is my x, this is my y right here, substitute them back in. So negative 2 times negative 2 is 4, plus 2 gives me 6. It works in the first equation. Try it in the second equation. 3 times 6 is 18. 18 plus negative 2 does give me 16. We know that it is a solution to both of them, so we know we have our answer. All right, let's look at a couple other examples, because you'll notice in number 3 that something's a little bit different here. If you look in this one, you'll see that neither equation has a variable by itself. So your goal here now is to get one equation to have a variable by itself, because we want two things that are equivalent, that you can take one and substitute it into the other equation. So we either want the x equals or we want it to be a y equals. Now, usually when you use substitution, the only reason you would choose substitution is if you can do that easily. So when I look at this, looking at kind of the different variables that I have here, one of these variables stands out to me. when I look at this second equation right here, I see that the y is almost by itself. Now, this isn't the only one that you could choose. There's lots of different options, but to me, that one's the easiest one to get the variable by itself. Now, I could have done that up here if I got, the y by itself. You could subtract 4x and then divide everything by -2. But to me, I'm like, well, that takes more work. Why do I want to do all of that work when I could just do one step? Like here, all I have to do is subtract 2x and the y is already by itself. Now again, you could have picked x's to solve for. However, if I pick either of these on here, like say I pick the second one to solve for x, we would subtract the y and divide by 2. We're going to get fractions. Now, I know we love fractions. Fractions are our friends. I always say that. However, when you're going through a longer problem like this, do you really want to deal with the fractions? I'm going to say probably not. So I'm going to skip the fractions and go with the ones that are easiest. So since I solved this equation for y, this is what y is equivalent to, that -2x minus 3. And I'm going to replace that into this equation here. So I'm going to rewrite this. So 4x minus 2 times -2x minus 3. And that is equal to 14 right here. Okay, so now we have an equation that just has one variable here. Again, this is what I replaced in there just to make it stand out a little bit. And now we can just solve it. So if I go through the solving, we get 4x. Be careful with the negative. Distribute that. That's sometimes the biggest mistakes I see on these are just multiplying, dividing, adding, and subtracting mistakes. I do it too, so take your time. So we combined our like terms now. I'm going to start to go quicker. Subtract the 6, divide by 8, and we get x is equal to 1. Now, once we have that x coordinate, same thing holds true. We're going to substitute it back in to find the y coordinate. Now here, you could solve it or substitute it back into the first equation. You could do it into this standard form equation right here, or I'm going to choose to put it into the one that I already solved, because again, I already did that little bit of work to put it into a y equals right here. So I already have the y by itself, and now I get my y coordinate. Okay, again, I'm going to go through a couple more just to kind of make sure we have this down. There's going to be some different special cases here as well. Now, when I look at number 4, yikes, this top one looks a little bit messy, right? So when I see this one, I might maybe even put both of them into standard form right away. You may or may not notice the standard form. You may notice a variable that's easy to solve for. Again, there's lots of different ways to do it. I'm going to do standard form for both of them first. So I'm going to subtract 4x. That gives me x plus y. I'm going to subtract the 2, and that gives me 5. And then right here, I'm going to put this one into standard form as well. I'm going to subtract the 5y, so we get 7x. And notice that's going to be minus 9y is equal to 3. I typically like to kind of get everything together. Now, on this one, you have a couple different options. Do you want to get the x by itself? Do you want to get the y by itself? Totally, completely up to you. I would say both of them are equally easy on this one here. So completely your choice, whichever one you want to go with. I'm going to, I don't know, choose to solve for y. And that gives me that y is -x plus 5. And we're going to put that into the y in the second equation. Again, I like to get them all into kind of a nice and easy form. Technically speaking, you didn't need to do that here, but then you would need to replace it in the y twice. And why would you really want to do that when it's just as easy to combine your terms together? So I replaced it. Let me make this stand out here. That -x plus 5 inside for that y on this equation here. So now we're going to go through and multiply it all the way out. So that gives me plus a 9x. A minus 45 is equal to 3. I'm going to combine my terms together. Add the 45. I'm going to start to go through this solving a little bit quicker just to make the video not quite as long here. So we get the x coordinate is 3. Again, substitute it back in. Do not skip that step. I'm going to talk about that over and over because that's a really common mistake. I'm again going to choose the one that I already solved for because it's nice and quick. Here, all you have to do is add those together and you have the y coordinate. All right, couple more here. If I look at number 5, definitely want to talk through this one because there's actually something a little bit different about this one that you'll notice. All right, to start it off, it's the same. Again, neither of them have an x equals or a y equals, but if I look at this first equation, pretty darn easy to get that x by itself. Again, not the only thing you could do, but to me that's the fastest. So now since that is equal to x, I'm going to replace the x in that second equation here. So that gives me negative 2y plus 4. And now I'm going to multiply it out. So negative 6y plus 12 plus 6y is equal to 12. Do you notice something kind of weird that happens here? Take a look at it. Notice that that negative 6y and positive 6y totally cancel out. We get an equation where the variable completely cancels out. I get 12 is equal to 12. Okay? Now, you have to kind of stop and look. We've done equations like this in a single variable before where it ends up looking like this. And typically what that meant in a single variable equation is that this would end up being, because this is true, that is true, that means that it would be all real numbers. If you remember anything from our video that we did earlier this week, we don't say all real numbers for a system because that's only if you have one variable. This one we have two variables. It's not saying that every single possible x and y value work in this system. It's saying that there are an infinite number of them. So that's how we're going to write our answer, that there are infinitely many solutions. Anything that works in one equation also works in the other equation. If you really go back and look at it, you might be able to kind of compare these two equations. If you look at these equations, if you were to divide everything in this second equation by 3, wouldn't you just get that first equation? So if you were to graph them, they would coincide, be exactly the same equation, the same graph. They intersect along the entire graph, and so that means that there's infinitely many solutions. Let's look at number 6 here. Here x is equal to 2y, so this one already has it by itself, so I'm going to use that one to save myself some time. I'm going to substitute that in here, so 3 times x minus 6y is 10. Instead of an x, I'm going to replace that with 2y. And let's multiply it here. There's only one thing to multiply, so it's not really distributing. Again, notice what happened. It's not always going to be a 6y that cancels. I don't know why both of these examples happen to have that, but 6y minus 6y, bam, those are gone. We get 0 is equal to 10. Does 0 equal 10? No, hopefully you're saying that out loud right now. No, they do not equal each other. Again, whenever those variables canceled and you get something that's not true, that means that there is no solution here. That is the same way we answer it for a system. This would have no solution. If you were to think about the graphs, you don't need to do this, but if you were to put them into slope-intercept form, you would get y equals 1/2 x. Here, when you subtract the 3x and divide by negative 6, you'd get y equals 1/2 x and then minus 10 over negative 6 right there. But if you notice that both of them would have the same slope, they would be parallel lines, which means that they never intersect each other. All right, so a couple more I want to look at because there's a couple more different cases just to kind of go through here. Let's take a look. All right, looking at number 7 here, looks kind of like a normal equation, and it is. Again, when I look at this first equation, I see the y that's really easy to get on its own, so I'm going to go ahead and just do that right away. When I look at this second equation, I'm like, ugh, it's got x's on both sides. Let's put it in standard form. Let's subtract the 2x and get 8x minus 2y is equal to 11. Just a little bit easier to look at. So we're going to take this equivalent to y, put it in for the y right here. So we get 8x minus 2y is 11. Again, instead of y, we're going to replace it with that negative 3x plus 5. And then we're going to multiply it out. So we get 8x plus 6x minus 10 is equal to 11. So that gives us 14x minus 10 is equal to 11. 14x is equal to 21. And we're going to divide by 14. And right about here, I get a lot of people that are like, ugh, oh, yuck, I did something wrong. I can't divide 21 by 14. But don't forget, you can divide any number by any number. It may not come out to a nice integer answer. We might get a fraction answer, and that is okay. That's one of the reasons that we need to learn methods like substitution or elimination, because again, it's not always going to be nice integer answers. So I hit that again. Okay. So when I look at 21 over 14, that's when now I want to think about how can I reduce that. I can divide both of those by 7 and we get 3 over 2. Yes, 1.5 is the same answer. I like to write them as fractions just so we get used to it that way. So yes, we do need to take that and substitute it in. So I'm going to go back up and look at my equation. I'm going to choose to put it into this one here. So y is equal to negative 3 times 3 over 2 plus 5. You can use your calculator to help you if you want to on this. I'm just going to go through it by hand. So that gives us negative 9 over 2 plus 5. We need a common denominator. That would be 10 over 2 is the same thing as 5, which means y is 1/2. So don't be afraid if you get fraction answers. You will get fraction answers. Sometimes they're messy fraction answers, but you will get them every once in a while. All right, last one of these that I want to look at before you'll notice 9 and 10 look a little bit different. Number 8 here. Now, the reason I want to go through one like this is I see that neither the x or the y have like a nice easy variable to get by itself. So here you might have to do like a little bit of like thinking ahead on which one might be the easiest one to get. Now, we're actually going to learn another method next week, another method that might actually be easier than substitution here, but I want to show you how you can use substitution. So when I look, I'm actually going to look at the second equation here first. If I were to solve for either x or y, I'm going to think ahead and go, wait a minute, okay, I would have to subtract that, but I didn't have to divide by like 3 or divide by 4. And do those divide nicely by 3 or 4? No. So I'm going to think, all right, I'm not going to solve this one for anything. I may look at this one instead. So looking at this one, I'm like, well, okay, wait a minute. I can easily solve for either the x or the y on this one. Now, when we're going through it, again, it's kind of your choice here which one you'd want to do. But if I think about what I can divide by, I want to try and think how I can get the least amount of fractions. If I were to divide everything by 8, which was what I would do if I would get the y by itself, I would get a fraction here and get a fraction here. We don't really want to mess with the fractions. So I'm going to say, let's try and get the x by itself here. So I'm going to say, all right, let's subtract the 8y. That's a negative 28, sorry. Negative 28. And then divide everything by 4. And notice, sorry, this got really sloppy here. Notice we get nice, easy numbers. So if that's your, only option, you want to try and get the least amount of fractions possible. Could you deal with the fractions? Absolutely. But again, we want to try to do our best not to. So I'm going to go through the rest of this pretty quick. Again, you can solve it exactly the same. Make sure I don't go too quick and make mistakes on here. That gives us negative 2x minus 21 is negative 11. I'm going really quick here. Double check my work that I'm not too fast here. That gives us that the, oh, see, I already made a mistake. Go back and look. I went way too quick here. This is a y. Hopefully you noticed that here. That's a y. So this is a y, this is a y, this is a y, this is a y. Sorry about that. See, this is what happens when you try to go too fast. We get that the y coordinate is negative 5. And now we want to plug it back in and solve for the x coordinate. Again, I'm going to put it into this one. and we get 10 minus 7, or the x coordinate is 3. Sorry, see, that's why I always say don't go too fast. I went too fast and I made a mistake. All right, last couple that we're going to look at here. I know these are kind of long, but it's a lot of stuff to go through. The homework itself is not too bad here. So let's take a look. Notice we have a linear equation and a quadratic equation here. So we've so far solved one with linear and quadratic by graphing, but here I want to show you how to do it with substitution. Now, really what you could do is you could take the linear equation and substitute it into the quadratic, or you can take the quadratic and substitute it into the linear. Now, what's actually usually easiest is to take the quadratic and put it into the linear. Otherwise, like if I were to solve it for x, I'd be left with all the I'd have to square that x and put it in twice. If I solve for the y, that wouldn't be too bad. But I usually like to take the quadratic. It's usually easiest to take the quadratic and substitute that one into the linear. Again, not required, but typically from experience, it ends up taking less work. So notice I'm taking that entire quadratic and substituting it in. Let me show it a little bit different color here. So this entire thing is substituting wherever there's a y. Really be careful in this particular one that if it's x minus that y, you want to make sure you distribute that. So we get minus x squared minus 6x minus 7 is equal to negative 7 here. So I'm going to combine some terms together over here. But notice that you are going to get a quadratic equation here. So I have a negative x squared, a minus 5x minus 7 is equal to 7. All right, so we're going to get a quadratic equation. This requires us to remember stuff from our last unit. How do we solve quadratic equations? Now, when I look at this, let's get the c values over here kind of together. If I add 7 to both sides, notice, squared minus 5x is 0. Notice on this one here, we get equals 0 here. So we only have two terms. So we can think about all of our different methods and how we use to solve these. We could solve by factoring. We could use quadratic formula. We could use completing the square. I'm not going to because that's an odd number here. We can't use square rooting on this because we have an x squared and an x. Really, when I look at this one, factoring is probably going to be my easiest. So I'm actually going to factor out a GCF of negative x, and we're left with a positive x, and notice that would be a plus 5. So since I'm solving it by factoring, now we can set them equal to 0, and we get two answers. We get x is 0, and we get x is negative 5. So that actually means we have two solutions. If you think back to when we graphed these, a lot of times a line and a parabola intersected twice. So we have two solutions. So now we can take this and substitute it back in. Again, it's your choice here if you want to substitute it into the linear one, if you want to substitute it into the quadratic. Some people find the quadratic easier because the y is by itself. Some people find the linear easier because you don't have to worry about the squareds. Kind of totally up to you. I'm actually going to do the quadratic because the y is by itself here. So we get y equals, this one's particularly easy, doing 0. 0 squared plus 6 times 0 plus 7. So we get y is 7. Notice that, 7, that corresponds to the 0 here. And then I'm going to do the same thing here. Y equals negative, equals negative 5 squared plus 6 times negative 5 plus 7. So we get 25 minus 30 plus 7, or negative 5 plus 7, or 2. And we have our two solutions. Let's do one more like that. Again, if I look at this one, technically speaking, I could solve this for x, I could solve it for y and substitute it in, but typically I like to take my quadratic and substitute that into the linear. I typically find that's the easier way to do it. So wherever there is a y, I am replacing it with that x squared minus 5. So we get negative x plus 3x squared minus 15 is equal to 15 here. I'm going to rewrite it. So I'm going to put the x squared first minus x. Now be really, really careful right here. I tend to see a lot of people say, oh, there's a 15 on both sides. I can just cross those off. There's not, because if I subtract 15, we actually get 3x squared minus x minus 30 is equal to 0. So it is not just the 15s cancel out here. So again, we can think about different methods to solve it from our last unit. This one, I will tell you, does factor. If you couldn't factor it, you could also use quadratic formula. So good review of what we did in our last unit. I'm going to factor it. So we need numbers that multiply to 30. If you put a positive 3 here and then negative 10 here, that gives you 9x minus 10x. That gives you the negative 1x that we need. So 3x minus 10 is 0. X plus 3 is 0. Sorry, it's a little sloppy. Here we get 10 thirds is one answer. That's a 3. And we get negative 3. So we have 10 thirds is our x coordinate. Negative 3 is an x coordinate. And again, we want to find our y coordinate. Totally up to you which one you want to put it into. I'm going to do the quadratic again just because I think it's not too bad. I know people get scared off by squaring a fraction. You can use your calculator to help, or honestly, just do it in your head like that. So here we need a common denominator. Sorry, it's kind of blending together here. That gives us 45 over 9. We get 55 ninths. It's okay to have messy answers. And then here, negative 3 squared minus 5. This one's a lot easier. We get 9 minus 5, or 4. So a good review of some of our quadratics from our last unit as well.